4.54 billion years. Just let that number sink in for a second. It is a staggering, almost completely incomprehensible amount of time. If you were to sit down and count one number every single second, it would take you over 140 years just to reach 4.5 billion. It's truly mind-boggling. So you might be wondering, how in the world did an absolutely hellish, chaotic ball of boiling magma floating in the dead vacuum of space actually transform into the vibrant, breathable blue oasis that we call home today?
Well, welcome to This Explainer. Today, we are going to embark on a truly epic chronological journey. We're going to trace our planet's entire history, starting all the way back from its fiery, violent birth, watching it transition into a lush biological haven, and then eventually looking ahead to its inevitable, dramatic oblivion. Now, I know it's a massive story, but don't worry, we're going to take our time. We'll break down every single concept, use some fun analogies, and really dig into the details so you can truly grasp the immense scale and the sheer wonder of our planet's deep time journey. To make this massive history manageable, we've broken it down into 6 easy chapters. The birth of the solar system, a fiery early Earth, water and cooling, the spark of life, supercontinents and complex life, and finally, the future of Earth. Let's dive right in with Chapter 1, Birth of the Solar System. Okay, so it all starts with something called the nebular hypothesis. This is essentially the cosmic recipe for our entire solar system. Picture this, a massive, freezing cold, dark cloud of cosmic gas and dust just floating in space. As this ancient cloud started to spin, it began to flatten out. Think of a pizza maker throwing a ball of dough into the air and spinning it until it flattens into a massive disk. That's basically what happened, but on a scale of billions of miles. Now, gravity acted as the ultimate glue here, grabbing onto that dust and slowly clumping it all together over millions of years. The heavy, rocky, metallic materials, the stuff that could actually survive the intense, blistering heat of the newly forming sun, condensed close to the center. And that right there gave us our rocky planets, like Earth. Meanwhile, the lighter, fluffier gases got essentially blown further out into the freezing depths of the solar system, clumping together to form the massive gas giants we know today, like Jupiter and Saturn. Moving on to Chapter 2, a fiery, chaotic early Earth. You really have to imagine the early solar system as a chaotic, wildly dangerous cosmic shooting gallery. Around 4 billion years ago, during a period aptly named the Late Heavy Bombardment, the Earth and the Moon were just relentlessly pummeled by space rocks. We're talking non-stop asteroid impacts. Now here's a really interesting fact. Earth actually took way more hits than the Moon did, simply because Earth is bigger and has a much stronger gravitational pull. It literally pulled the danger right toward it. But if you look at the Earth today, you don't see those craters, right? That's because Earth has plate tectonics. Our crust is constantly shifting, melting, and recycling itself, which acts like a giant eraser, scrubbing away our ancient scars. The Moon, on the other hand, is completely geologically dead, so its cratered, battered surface acts as a perfect, frozen museum, preserving the sheer violence of that era for us to see every time we look up at the night sky. And the violence didn't stop at just asteroids. During this chaotic time, Earth experienced a collision so unimaginable, it almost defies description. A completely separate Mars-sized planet, scientists call it Theia, smashed directly into the early Earth. This impact was so monumentally violent that it didn't just leave a dent, it literally vaporized billions of tons of solid rock on the spot. It took both planets and spun their debris into this incredibly bizarre structure called a synestia. If you're wondering what that is, imagine taking 2 molten balls of clay and smashing them together so hard and fast that they spin out into a giant, glowing, molten cosmic donut floating in space. That's a synestia. Eventually, over a very long time, this incredible fiery donut began to cool and coalesce, pulling back together to form both the newly reborn Earth and our Moon. When you look at how things played out, you realize we are just incredibly, unbelievably lucky that Earth evolved the way it did. To put this into perspective, let's look at Venus.
Venus is often considered our sister planet because it formed in the same neighborhood, from the exact same cosmic cloud of dust. But their fates couldn't be more different. While Earth's surface temperature averages a very pleasant 15 degrees Celsius, Venus is a toxic, suffocating hellscape baking at 477 degrees Celsius. That is literally hot enough to melt solid lead on the surface. Venus suffered what we call a runaway greenhouse effect, getting crushed under a heavy, toxic atmosphere made of 96% carbon dioxide, and on top of all that, it even suffered its own massive cosmic impact at some point, an impact so severe that it knocked the planet completely upside down. It now rotates backwards, and it spins so agonizingly slowly that a single day on Venus actually lasts longer than its entire year. When you compare that to our beautiful blue marble, it's clear we truly won the cosmic lottery. Just to keep us oriented in this vast ocean of deep time, we're now transitioning out of the hellish Hadean Eon. And honestly, it's aptly named after Hades, the Greek underworld, because it was literally hell on Earth. As we move our timeline forward, we'll enter the Archean Eon, which is where life finally begins to emerge, then the Proterozoic Eon, where complex life slowly takes shape, and finally our current era, the Phanerozoic Eon, which translates to the era of abundant visible life.
That brings us to Chapter 3, Water, Zircons, and Cooling.
So for a very long time, scientists assumed that Earth stayed a boiling, molten ball of magma for a good 500 million years after it formed. But science is always evolving, and we recently found something amazing: zircons. Now, zircons are microscopic, nearly indestructible crystal time capsules. We're talking tiny, no bigger than the period at the end of a sentence. But despite their size, they hold massive secrets. By analyzing the chemical signatures locked inside these tiny crystals, scientists proved that Earth actually cooled down, grew a solid rock crust, and even had pooling liquid water up to 400 million years earlier than we originally assumed. Think of it like a hot fruit pie coming out of the oven and slowly forming a cooler crust on top while it sits on the windowsill. That's our early Earth, cooling down much faster than anyone guessed.
But that discovery leads to a really massive scientific mystery. Where did all that water actually come from? We're at Water World, but how did it get here? Well, it's actually a huge debate in the scientific community. One theory is volcanic outgassing. This is the idea that water vapor was trapped deep inside the Earth's mantle and was essentially just burped out through thousands of volcanoes over millions of years. Another theory is that it was delivered from space. Imagine a cosmic delivery service where specific meteorites or massive barrages of icy comets continually crashed into the planet, dropping off water ice with every impact. Or there's a fascinating chemical theory. What if the early massive magma ocean simply interacted with molecular hydrogen in the atmosphere and they basically just manufactured water right there on the surface? The reality? Our massive, deep blue oceans are most likely a spectacular combination of all these incredible processes working together over deep time.
Which sets the stage perfectly for Chapter 4, the spark of life.
Now that we have a cool, wet planet, we get to the most miraculous leap of all, going from simple, non-living chemistry to living, breathing biology. How did that happen? Well, one leading theory suggests life began deep, deep down at the bottom of the ocean at hydrothermal vents. These are basically natural underwater chemical reactors fueled by the Earth's escaping internal heat. Warm, dark, and rich in minerals. But another incredibly compelling theory points to shallow surface ponds. Imagine these little pools on the early continents undergoing intense wet and dry cycles. Because Earth didn't have an ozone layer yet, these ponds were absolutely blasted by the extreme, deadly ultraviolet radiation of the sun. It basically acted like a brutal obstacle course for early chemistry. Only the absolute strongest, most UV-resistant chemical bases could survive that constant radiation barrage. And those incredibly resilient survivors, they went on to become the very building blocks of our RNA and DNA. The tough survived, and they literally built us.
So once life finally got going, it didn't just sit there. It literally changed the entire planet. Enter cyanobacteria. These are tiny, unassuming, single-celled organisms that managed to figure out an incredible biological trick: photosynthesis. They started using sunlight for energy, and as a byproduct, they began pumping massive amounts of oxygen into the atmosphere. But here is the massive, ironic twist of this era. For all the older anaerobic life forms, creatures that had evolved in an environment completely without oxygen, this new gas wasn't a breath of fresh air, it was deadly, toxic pollution. This is known as the Great Oxygenation Event, and it caused a massive global extinction. Furthermore, all this brand new oxygen reacted with the atmospheric methane, which had been acting as a cozy greenhouse blanket for the planet. By destroying that methane blanket, temperatures plummeted, triggering the very first snowball Earth ice age. So life's greatest, most incredible innovation, photosynthesis, almost literally froze the entire planet to death.
As the ice eventually thaws and the atmosphere stabilizes, we move to Chapter 5, Supercontinents and Complex Life. One of the most fascinating things about Earth is how its geology and biology are deeply, intrinsically connected. Plate tectonics didn't just move rocks around. It acted as a massive, unstoppable evolutionary engine. Over hundreds of millions of years, land masses constantly crashed together to form giant supercontinents, like Rodinia and later Pangaea. Then they would rip apart again. Every time they ripped apart, they created vast new shallow water coastal environments, opening up brand new real estate for life to adapt to. Meanwhile, down at the microscopic level, complex cells invented sexual reproduction. This was an absolute game changer because it wildly accelerated genetic diversity. When you combine this perfect storm of constantly changing physical habitats with this new, rapid genetic mixing, it fueled what we call the Cambrian explosion. This was quite literally a biological Big Bang. Suddenly, over a relatively short geological time span, the ancestors of almost all modern animals suddenly appear in the fossil record, developing eyes, shells, armor, and eventually getting brave enough to crawl out of those shallow oceans and take over the land.
And I want to pause here because this deep time history directly impacts your everyday life right now. Let's look at the Carboniferous period. Back then, vast, sprawling, swampy forests covered huge portions of the land. When those bizarre, alien-looking trees and plants died, they fell into the swamps. They didn't rot normally. Instead, they were buried under mud and rock, and they were compressed over hundreds of millions of years. Do you know what those ancient dead plants became? They transformed into the massive coal and fossil fuel deposits that humans eventually dug up to power the entire modern industrial revolution. So think about this. When you turn on a light bulb in your house today or plug in your phone, you are very often using solar energy that was captured by a tiny leaf over 300 million years ago. It's practically time travel.
Finally, we reach our last chapter. Chapter 6, The Future of Earth. You see, the planetary tectonic engine is still running, and it doesn't care about us. In the distant future, hundreds of millions of years from now, the continents are going to smash together once more to form a brand new supercontinent that scientists call a Maja. But this massive, single landmass is going to cause some huge problems. It will drastically alter the global carbon cycle. Because of increased rock weathering on this giant continent, atmospheric carbon dioxide levels are predicted to drop precipitously low. And what happens when CO2 drops too low? Plants will no longer be able to perform photosynthesis. It's that simple. When the plants inevitably die off, the herbivores have nothing to eat and they die. Then the carnivores die. The entire complex food chain completely collapses, slowly and inevitably starving the surface of all complex life.
But ultimately, long after that, Earth is going to face a catastrophic mechanical failure. Remember that liquid iron core deep in the center of the planet that generates our protective magnetic field? Well, that core is slowly but surely losing its heat. When it eventually cools down and solidifies completely, the planet's magnetic dynamo is going to shut down for good. Our invisible magnetic shield will simply vanish. Without it, the intense, violent solar wind from the sun is going to relentlessly blast our planet like a cosmic sandblaster. It will slowly strip away our oceans, blowing our entire atmosphere straight out into the void of space. Earth's surface temperature will wildly spike, and incredibly, tragically, our beautiful blue oasis will end up looking a whole lot like that dead, toxic sister planet we talked about earlier, Venus. Which leaves us with a truly profound question to ponder. Are we just a fleeting, miraculous spark in a 4.6 billion year cycle of absolute cosmic chaos? When you really think about it, from a violent fiery collision in a nebula to a frozen snowball Earth to this one brief fleeting moment in deep time where intelligent life can actually look back and understand its own origins, our entire human existence is just a tiny microscopic sliver in an immense, unfeeling cosmic narrative. It's humbling. It's a little terrifying, but honestly, it is also incredibly, wonderfully beautiful. Thank you so much for taking this deep time journey with me today.